Hi, I'm Bob Dobkin. I'm the CTO at Linear Technology. I want to talk a little bit about accurate temperature measurement. Because for accurate temperature measurement, we have to have the inaccuracies of the electronics and the inaccuracies of the sensors compensated for. With the LTC 2983, we can get very accurate temperature measurements. Most of the inaccuracies are going to come from the sensors. We have three major temperature sensor types. We have resistance sensors, which can be either platinum or a thermistor. We can have thermocouples, which have a multitude of different wires, and the output of a thermocouple is proportional to temperature difference. And we can have diodes and transistors. The sensors themselves don't read out temperature. We have to convert some parameter of the sensor into temperature to get a temperature measurement. They'll read out either voltage or resistance, and we have to measure that and convert it. Well, how good are these sensors when we first get them? You buy a platinum sensor, you buy a thermistor, you buy thermocouples, diodes and transistors you get out of the junk box. The platinum sensors, they can be anywhere from 0.3 degrees to 1.5 degrees as manufactured, because it's the length of the platinum resistance that's in there that changes. Thermistors are an oxide composition, and they're actually trimmed at manufacture, and you can buy those to 0.1 degree C accuracy as manufactured. Diodes and transistors, 1 to 2 degrees. We have circuitry in there that compensates for some of the errors within a diode as a temperature sensor. Thermocouples put out microvolts. Their output is proportional to the temperature difference between the cold side and the hot side, and they actually generate voltage. The error is usually specified at max temperature differential, which is different for different thermocouples, and can be anywhere between 1 and 4 degrees for an uncalibrated thermocouple. But if a thermocouple has a 400 degree C range and you're only measuring 100 degree C, you have 1/4 of the max error because you're not using it over the full range. Diodes and transistors are not manufactured to be temperature sensors, but the diode and transistor characteristics are very consistent with temperature, and that can be converted into temperature. For calibration purposes, if you need to calibrate some sensors, you can either buy an expensive system that's traceable to National Bureau of Standards. You can also buy some mercury and glass thermometers. These can be bought calibrated to better than 1/10 of a degree, and in a water bath or an oil bath, they provide a pretty good standard for calibrating other types of sensors. The measurement architecture of the LTC 2983 is to try to minimize the errors in the electronics. We're trying to get the best accuracy and conformity we can get between the input from a sensor to an output in digital temperature. So we've got architectures that try to minimize these errors. With a resistance sensor, you have to reverse the sensor current periodically, or else you'll get thermocouple errors from the sensor because the wires in the sensor generate thermocouples. You also have to keep the power low in the sensor, or else you'll have self-heating effects. Thermocouples, they put out very low microvolts, so you need amplifiers and circuits that are auto-zeroing so they do not add any additional error to the thermocouple. For measuring resistance, we don't measure the resistance directly. We measure the ratio of the resistance of the sensor to a standard high precision resistor, and that gives us the best accuracy for measuring the resistance and therefore the temperature. When we've got these temperature sensors, we have to do a lot of correction to turn the output into a real temperature. The sensors are not linear. They have offset. If this is the perfect sensor, they can be anywhere in a range. They need a scale factor because their output in terms of millivolts or microvolts per degree C is not always the same. So we have to provide offset correction, scale factor correction, and linearity correction. And that's all done in a digital processor in the 2983. So we aim to get the best accuracy we can in the electronics so that we throw all the inaccuracy back into the sensor. We call our device 0.1 degree C accurate, but it's really 0.1 degree C conformity because we can't tell you what the sensor accuracy is. We have a lot of sensors come with calibration tables. We have some RAM in our processor so that you can put in custom linearization and scale factor for the different sensors. And you can end up with much better accuracy than the as manufactured sensors will give you. This is a partial block diagram of the LTC 2983. We have three 24-bit A to D converters. We need these because of the very large dynamic range with thermistors. They're also auto-zeroed so that we can get accurate measurement of thermocouples. It has 20 inputs, so you can use them differentially or single-ended. Has a built-in voltage reference, and it has a big processor in there to take out all the nonlinearities. Inputs are buffered, so you don't have to worry about the 2983 loading the sensors. We've got a lot more information about the LTC 2983 on our website, www.linear.com. And we've got applications information with that as well. Thank you.